Hi. So for the last section of this particular chapter, we will look at the idea of locus. There are three types of locus that you need to study. So first of all, what is locus? Basically, this is a path that is being traced out by a point due to its motion following a certain pattern or a certain rule. So this particular rule can be due to equality or non-equality or inequality. So let us look at what are the possible locus for complex numbers. The first one is being the circles. So you have three conditions. Basically, the first condition is when the modulus of z equals to r. So this represents the circumference of a circle. The center will be at 0, 0. The radius will be equals to r. So why is that so? From the definition of modulus, we know that modulus z will be equals to square root. So let's say z equals to x plus iy. So modulus of z equals to, this is by definition, square root of x squared plus y squared, and this is equals to r. So x squared plus y squared equals to r squared, and this is the equation of a circle. Center at 0, 0, radius will be r. So if you see modulus of z smaller than r, okay, so for this diagram, what you will need to draw is this. If you see the modulus of z smaller than r, basically you already know that this represents a circle center at 0, 0 with the radius r, but because there is no equality over here, so you cannot include the boundary of the circle, which is the circumference, and you need to shape the circle inside because this is smaller than r. So the third case will be when modulus of z is smaller or equals to r. So in this case, because of the equality sign, you can include the boundary, which is the circle by itself, and then you need to shape the inside as well. So basically that's the idea of circles using complex numbers. So of course, previously when we studied about circles, we did study the equation when your center is at somewhere else. So in this case, we can do the same thing. So basically, let's say, point number 4. So you can also have z minus some point z1 equals to r. So in this case, I will let z1 equals to a plus bi, for example. So if that's the case, when you expand everything out, So by definition, this will be the square root of x minus a, the whole thing square, and then y minus b, the whole thing square equals to r. So you have x minus a square plus y minus b square equals to r squared. So this is basically the equation of a circle with your radius r and center at AB. So I will just write the description once. So this will be the equation of a circle, center at AB, the radius is r. So similarly, so if you want to draw the diagram, for example, so sorry, let me draw it properly. So let's say this is your point AB. So this will be the diagram that you need to draw. Then if let's say you have modulus of z minus z1 smaller than r, so what you need to draw is something like this. So you have your point here. Because there's no equal sign, so you need to draw the dotted line of your circle and then highlight all the content inside. So if you have z minus z1 smaller or equals to r, then you can draw something like this. Draw a solid line, solid circle, and then highlight everything inside. So basically, this will be the equation of circles through the idea of complex numbers. So now let's look at the second case of locus of a complex number, which is called the half lines. Okay, so what is the idea of half lines? Let's say when you have the argument of z equals to some angle theta, so usually what you would draw is something like this. So let's say this is your z, this is your theta. Okay, so depending on the value of theta, basically your line can be either going to the first quadrant, second quadrant, third quadrant, or the fourth quadrant. So this is what we call as half line, because you start from your origin and you go to the point that you want to go. So generalizing this kind of idea into locus, so what you would have is something like this. The argument of z minus some point equals to some angle theta, for example. Okay, so in this case, z will be equals to x plus yi. Z1 will be equals to a plus bi, for example. So how do you interpret this kind of equation? So what you can do is as follow. you assume that z equals to x plus iy, and then z1 equals to a plus bi. So what is z minus z1? This will be x minus a plus I multiplied with my minus b. So then, by definition of the argument, we know that this is equals to the inverse tangent of y minus b divided by x minus a. Okay? And from what we have defined in the first line, this is equals to theta. So then you can sort of like perform the tangent on both sides, so that you get y minus b divided by x minus a. This is tangent theta. So finally, what you can do is to write everything to the right hand side and then let it become some equation of lines. So you have y equals to tangent theta multiplied with x minus a, and then plus b. So this is basically an equation of line. So in terms of diagram, how would you draw it? Basically, what you need to do is to identify where is your point AB. So let's say your point AB is here. This is Z1. So if you encounter this kind of equation, what you will need to do is to draw a dotted line. And then please remember that usually you don't include the endpoints, because if let's say so Z1 is A, B. So if let's say your Z equals to X, Y, and this is A, B, then basically you don't have any complex numbers for you to plot the lines. So usually we would avoid this particular point, which is why we need to draw the open circle, and then you just go up. So this will be your locus, and your angle will be theta over here. So now in the textbook, they also introduce this particular notion, the argument of Z1 minus Z. So how would you actually handle this kind of equation? Okay. So what I would do here is as follow. We know that argument of Z1 minus Z. So let's keep this for the moment and let's go over here. If let's say you have argument, okay, so the goal here is to see what is this particular equation. So argument of Z1 minus Z is equals to the argument of minus Z minus Z1. So which means that we can rewrite the whole equation if let's say we know argument of Z equals to theta. So what happens when you have argument of minus Z? So essentially, if let's say we know the argument of minus Z in terms of theta, basically we can just make use of what we have known before and deduce what is this particular form. So there are a few ways for you to do that. Over here I will show the algebraic way. So first thing first, what is minus 1? If you think about it, minus 1 is equals to e to the power of I pi, because when you write into the Euler's equation, so you have cos pi plus I sine pi. So sine pi is 0, cos pi is -1. So -1 basically is e to the power of I pi. And this can go repeat every 2 pi, for example. So now if let's say you let z equals to r e I theta, then minus z would be r e I theta plus pi. Of course you can also minus pi, but in this case we can just use plus pi and then figure out the direction, for example. So then argument of minus z will be equals to the argument of r cos theta plus pi plus I probably don't have enough space, so I need to move this particular equation to the left. Plus IR sine theta plus pi. So we know that the definition of argument is just the inverse tangent of R sine theta plus pi divided by R cos theta plus pi. And you can cancel off the R. Sine divided by cos is tangent. So in the end, what you will get is just theta plus pi. But we don't end here for the moment. So what is theta plus pi? So if let's say this is your angle, this is theta, when you plus pi, it actually goes down, right? So previously we also know that the principal arguments ranges from minus pi to pi. So we cannot define this particular angle. We have to define in the opposite direction. So the opposite direction will be minus pi minus theta. Hence, this is also equivalent to minus pi minus theta. So algebraically, you can perform this kind of operation to show that the argument of minus z is actually minus pi minus theta. Geometrically speaking, you can see that whenever you have this kind of operation, you can rewritten this into z minus z1, and you try to transform using this equation. So the argument of z minus z1 would be minus pi minus theta. So geometrically speaking, before this, when you have argument of z minus z1 equals to theta, you draw the upper part of your line. So now, because of this particular diagram, let's say this is your point, which is z1. Sorry. Of course, you still can't include the endpoint. So if the argument of z minus z1 equals to theta, you point up. So then this time you point down. So what would be the angle? The angle would be minus pi minus theta. So that's how you figure out what is the locus for this particular set of equation. So later on we will look at some examples. So now finally, the third type of locus is what we call as the perpendicular bisector. And this is of the form z minus z1 equals to z minus z2. So you can easily see that the left part is modulus, right part is also modulus. It means that the distance between your locus with respect to the point z1 has to be the same as the point z2. So let's say you have z1 over here, z2 over here. So basically, you just need to find the midpoint between z1 and z2. Find the midpoint. And then the next step is to find the angle between z1 or z2, or the gradient of z1, z2 as a line. And then use the perpendicular formula to find this particular equation. So this will be modulus z minus z1 equals to z minus z2. Okay. So you can also have this kind of case. For example, z minus z1 is smaller than z minus z2. So in this particular case, then what you would have is something like this. So the distance of z to z1 so we still draw this thing. Okay, so here you need to be careful because there's no equality sign, so you need to draw the dotted line. So now the distance from z1 is smaller than the distance from z2. So this is the region that you need to shave. If let's say you have z minus z1 smaller or equal to z minus z2, so this time what you would do is to plot these 2 points, and let's say this is your perpendicular bisector. Because there's equal sign, you can draw a solid line, and then you just shave everything here, because the distance from z1 is smaller than the distance from z2. So that's basically it for the last section, which is on locus. So now let's look at some examples. Sketch the followings. So the first one, if you have the modulus of z plus 4 minus 5i equals to 2. So always remember, convert this to a negative sign. So you have minus 4 plus 5i. So it means that perhaps I should draw like this. This is minus 4, 5. And you have a circle like this. So if let's say I write z plus 4 minus 5i smaller than 2. So in this case, you would have something like this. So because there's no equality, so you draw a dotted line. And then, sorry, don't forget you need to shave it. So if you have z plus 4 minus 5I is smaller or equals to 2, what you would have instead is something like this. You draw a solid line and then you shave it. So that's for the circle. Now let's look at the half lines. If let's say you have argument of z minus 2 plus 3I equals to pi over 12. So we know that we need to write the minus part. So you have 2 minus 3I. So in this case, it's not that difficult to understand, because essentially what you need to do is to start from 2 minus 3. Sorry, remember to draw the open circle. This is 2 minus 3. And then you go up. And this angle will be pi over 12. So that will be your locus. Now let's look at the argument of z by, let us do this, 2 minus 3I minus z. So you are still letting it to be equal to pi over 12. So first thing first, rewrite everything. You put a minus sign here. Z minus 2 plus 3I. So previously we already see that z minus 2 plus 3I is exactly this. So the minus part, we know that on the right, what you actually need to draw is minus pi minus this particular angle, which is minus 11 pi over 12. So then what you need to draw is something like this. So the point is still 2 minus 3I. This will be your horizontal axis, which is parallel to your x-axis. And this will be minus 11 pi over 12. So you can see that the difference between these two angles, basically one is going up, half of it, the other one will be going down, which is also half of it. Okay. Of course, if let's say the question directly give you, for example, the argument of z minus 2 plus 3I equals to minus pi over 12. If it already converts it for you and you always begin with z, so you don't need to do all the complicated conversion like just now. And you can directly start with minus 2, 3, sorry, 2 minus 3. This will be minus pi over 12. So understand the difference. I would recommend to, whenever you want to solve the half-lines questions, always start with z. Whenever you meet this kind of equation whereby your z has a negative sign, always try to convert it back to the positive, like these two steps, so that you know what you are drawing exactly. Okay, so now let's look at some examples of perpendicular bisector. So you have z minus 10 equals to z minus 6i. So then what you need to draw is something like this. You have 6i over here and then 10 over here. So this will be the line that you need to bisect. So let's say this is the, of course, in reality, when you want to calculate this, you need to find the midpoint. And then you need to find the gradient. Which we usually label it as M1. So over here, you need to find the equation of the line using the midpoint and the gradient. Also, you need to use M1, M2 equals to minus 1, for example. But now we are just sketching, so you don't need to be that accurate. So this will be the locus. So let's say if you have modulus z minus 10 is smaller than z minus 6i, what you will need to draw instead would be, so here's 10, here is 6i. You still draw the line, and then because there's no equal sign, you have to draw a dotted line. So in this case, the left side is smaller than the right side, so you find where is your 10, which is here. So you just shift everything to the right of your perpendicular bisector. So finally, if you have z minus 10 smaller or equals to z minus 6i, you draw the same thing. So this is 6, this is 10, draw a line, and then this is your, so now because there is an equal sign, you can draw a solid line and then shave it. So those are all the different examples that you can illustrate for the locus. So let's look at one final example before we end this chapter. For complex number z, which is satisfying this particular equation, 16. Find the smallest and the greatest possible value of z. So before you do this question, remember to sketch the diagram, because this is basically geometry questions. Okay, So the center will be at 816. 816. And the radius will be 2 root 5. So this will be the radius, for example. So what the question means is basically, let me move this a bit. Okay. So what the question asks is basically you need to find two of your complex numbers such that the modulus z is the smallest and the modulus z is the greatest. You need to find these two. So the idea is that basically if you draw a straight line connecting the center to the origin, this will be the smallest complex number, this will be the greatest complex number. So that's what we need to do. So first we need to identify the straight line, and then we need to identify the equation of a circle. So equation of a circle is not that difficult. Basically that will be given by let's say x minus 8 square plus y minus 16 square equals to the square of 2 square root 5. So that will be 20. So this, how do I derive this? Basically you use the definition of the modulus. So this will be our first equation. The second equation would be equation of a straight line. So y minus 16, sorry, the easier way is y minus 0, x minus 0 equals to 16 minus 0 divided by 8 minus 0. So y equals to 2x. So this will be our second equation. Substitute inside the first equation. Substitute 2 into 1. So what you would get is x minus 8 square plus 2x minus 16 square equals to 20. So now expand everything. You have x square minus 16x plus 64 plus 4x square minus 4 times 16 is 64x, and then you have 16 square, which is 256 minus 20 equals to 0. So you have 5x square minus 80x, that will be 320 minus 20, so you have 300 plus 300 equals to 0. So you divide everything by 5, you have x square minus 16x plus 60 equals to 0. So now factorize this. This will be 610. So then in the end you have x minus 6, x minus 10 equals to 0. X will be equals to 6 or 10. So now we know that y equals to 2x, so y will be equals to 12 or 20. So the smallest modulus z will be equals to 6, sorry, square root of 6 square plus 12 square. So this is square root of 180 and you can easily simplify it to 6 square root 5. So the largest modulus z will be the square root of 10 square plus 20 square. So it's square root of 500. So this will be 10 square root 5. So that's how you solve this particular question. So again, for locus, what is important is you need to be able to sketch all the different types of equations which is given to you. Okay, that's all for today. So we have finished P3 basically.